Hello there. I am recording this video for CSCI 3060. This is a lecture that unfortunately I had to miss because I was in the emergency room, so hopefully that's a good enough excuse. I am feeling okay, but obviously it was not a good idea for me to have come to class, and I'm got a big old bandage on my back to prove it. So let's talk about this topic so that you have some guidance for your quiz on Wednesday, and also because this is going to be a topic that's covered in some amount of detail on the final. So we're going to look at actually doing code inspections. Last class we talked about it in a very formal sense. In reality, a lot of code inspection is not done in a formal way, but needs to be done in some form. So we're going to look at a few different ways that it's handled, including checklists, paraphrasing, walkthroughs, different practices, whether they're lightweight or heavyweight, and how this is done with extreme programming, like it is for your project. So pair programming, refactoring, and different patterns of refactoring. So let's dig in. Now, even though there is a formal process, because these formal processes take so much time, we usually want to rely, when we can, on something a little bit shorter, or at least that doesn't require so many people meeting together, right? When you have a really big team and it takes a ton of people all to meet up, it's sucking a lot of time away because each of those people could be working on something else. So very often it's the case that we want to be able to do something a little shorter than the big formal review with multiple meetings and so on. And here are a few different options. So you have checklists, which a list you can check things off, paraphrasing, which helps to indicate your understanding of what the code is doing, structured walkthroughs, and formal proofs, which actually can take longer. It depends on the code, to be honest. So let's talk about checklists first. Checklists are pretty good because they have a list of objective things on them. Now, whether those objective things are good things or not is subjective, but I can say for not, like yes or no, there are no lines of code longer than 80 characters. Like it's a very binary kind of thing. And it's pretty helpful to have these because they help to indicate, like, does the code actually pass muster? So we want to look at desired properties, things we want the code to have. For example, does every method have a header? And undesired properties, no lines of code longer than 80 characters kind of thing. There can be simple ones, such as format, more complicated ones. Does the code terminate? Can you prove that the code doesn't have infinite loops? Can be tricky. We can't do this for all functions, but at least if you can do it for yours, that's a good thing. Generally, the person inspecting is going to look and see, is it there, is something there, is something not there, and check it off. And usually this is only part of it. You wouldn't just do a checklist for an inspection. You would probably include some other steps as well. For instance, just because the code terminates doesn't mean that it's right. So you also have to verify it's actually correct, which is maybe where you start using some test cases, or you use some other steps, maybe a walkthrough or something like that. So here's just a few different examples. You can take a look at some of these on the slides, of course, just to point out a couple. For all your variables, I mean, names, for instance, do they actually meet the standards that, for instance, your company might set? Slash, are they good names? If every variable name is just a letter, it's probably not ideal. They usually need to follow some specific format or at least some helpful descriptions, right? They should be descriptive. It's a good thing. For each method, for instance, again, names are obviously important. Do your methods actually have good names that meet conventions? Do they return what they're supposed to return? If they don't have any return, that's an easy way you can just check no, there is a problem, save yourself some time. Okay, more and more of these are around. You can take a look. There's plenty of these online. None of these is like the definitive, you must use this checklist, but it's good to have these kinds of examples. Okay, now in addition to checklists, we have code walkthroughs. And you can think of this as like a guided tour. Usually the tour guide, which is sometimes the author, at least in some of the cases I've done this, it has been, basically describes all the points of interest, like the most significant parts of the code, to help someone understand it who hasn't had a chance to read through the entire thing. So you're walking through the different paths of the code. If somebody wants to do X activity, what parts of the code they need to do. Usually the reviewers will do this in a more formal setting, and we call this a dynamic walkthrough, where the people who are reviewing the code will also walk through and say, okay, this is what the code does here and here and so on. In a less formal setting, you might have the author do it because of the person most familiar with it, but again, it kind of depends on it. You also can have this be a static thing where somebody just has comments written by the tour guide or the author into the code. And both of these are pretty effective, especially because a lot of the time you want to do one of these walkthroughs, not necessarily because you need to actually evaluate the code. And in fact, walkthroughs are sometimes less effective than inspection, although better than testing for finding specific bugs. But the thing is, often you want to do a walkthrough, not necessarily for the benefit of the code or the author, but actually for the benefit of the people who are going to use it. A lot of walkthroughs I've done were not necessarily because we were looking to like fix part of the code or anything like that, but so that we can get people to work on it who had not any understanding of what the code was like before. And these walkthroughs are a good way to get people onboarded to that. So this is a very famous static walkthrough. So this is, again, static walkthrough being where there are comments left behind to explain what's happening in different parts. And this really famous one is literally just a walkthrough of Unix way back in the ancient year of 1977. And it's literally just source code and commentary on Unix back from the day. And it's split into a couple parts. There's one that's a line numbered listing of the code with comments. And a detailed commentary that's in parallel with it. So you have the code here with the comments, and then you have on the side of it commentary about the code indexed by the line numbers, so you can read through both these things at the same time. And this is helpful so you can figure out, well, what's the meaning of these parts of the code? What's it going to do? What are all the variables represent? Where do they get defined? It turns out this was never published because it's a trade secret, which is kind of funny. But of course, just like lots of other things, leaks happen. And this got leaked out, and now it's actually training material, which is kind of neat. And it is a pretty big piece of code, so it's interesting to look through. Okay, now, formal inspections, very good at finding problems, but the process kind of sucks. You wouldn't want to have to go through all these meetings if you don't have to. So we have all these other things that we can try to do to minimize how many formal inspections we actually have to have. So we have semi-formal meetings, email reviews, the 4 eyes principle, XP's process of continuous inspections, and just white box testing. So semi-formal review meetings are kind of like the inspection one. The only difference is that you don't necessarily need a moderator. So with a formal process, you have to have a moderator. The moderator needs to be as impartial of a person as possible. And so this whole process, again, becomes more formal because the moderator needs to be there, make sure everything's happening, and so on. With a semi-formal review, you, again, keep it less formal. So the author is, going to pick who are going to review this. They can pick a moderator or not to verify and everything. But if there is no moderator, then the author is the moderator, effectively, and they just ask people, okay, please tell me what things I need to fix in my code, and they figure out how to sign it off. Obviously, this is much less, there are more problems with this, but this can go a lot faster because you don't have to have the whole, as many of the meetings. Disadvantage, of course, is bias is the biggest one. It's less objectivity because the person in charge is the person who wrote the code, so they may be less willing to listen to feedback, that kind of thing. And also there's no independent assessment. So for instance, if the author says, oh yeah, I definitely addressed all these issues, did they? Or do they want to say that they did and then actually didn't? So that means that you can have some issues if you don't have a trustworthy author, for instance. Okay, do people still fax? I actually don't know. But email, of course, still exists, and email communication can replace the whole formal process. So the author sends the code to everybody, and their comments just email back. That's it. Don't really need a moderator because it's all just via email, and it's all pretty straightforward. You just send to everyone any comments that you need to send around. It mitigates the need to actually be there for a physical in-person meeting, which is nice. But again, same idea as before, no moderator, less objectivity, less monitoring. Same thing with, how do you know the author actually listened to any of the advice and did anything about it? You don't really know. 4 eyes principle. You looked at it twice with your 2 eyes and 4 eyes. No. So 4 eyes principle is, basically working in pairs. So each person who is working on the code has another person who is going to inspect the code. So it's your 2 pairs of eyes make 4 eyes. Each of them is responsible for the code and the correctness, and both of them have to sign off. So this is beneficial. In small teams, it's been shown to be effective, and it kind of makes sense in that if your name is attached to code that you didn't write, you're going to be very, very cautious to make sure that you're not letting something go out there that has your name on it, which might have a bunch of problems with it. So you're incentivized very heavily to make sure it doesn't have any of those issues. And of course, vice versa, where each person who is inspecting stuff then writes stuff that's inspected by the other person. Okay, so the predecessor of XP used this idea of the 4 eyes principle. This idea of chief programmer teams is where you have these weekly meetings. The whole team is reviewing design, architecture, and so on once a week. This probably sounds somewhat like some of the practices we talked about earlier in the course. And these get continuously updated. So unsurprisingly, this is where we got into pair programming, which is also lightweight. You don't have to have formal meetings or anything. You just have two people next to each other, and they do that. Now, we'll talk about code refactoring in a little bit, but this is the idea of taking code that hopefully works and changing it to make it better. Not necessarily faster or anything like that, but at the very least more maintainable, more legible, more understandable, and overall just better. There's a few things we'll talk about that you shouldn't have in code that is going to be addressed by things like code refactoring. Now, also white box testing. When you manually do white box testing, you have to understand the code to do it, right? Now, automated systems will take care of some of this for you, but if you want to be manually writing a white box test for a piece of code, you can't do that unless you know what the code's doing. So in practice, a lot of defects are actually just found by somebody saying, I'm going to manually make a few white box tests for this code and see if it works, and you just find there's a problem because you've looked at it and you say, oh, I think this might lead to issues, and you try it, and of course it does. Okay, so if you go the other direction, instead of going to lightweight and go to more formal than formal inspection, you end up with basically proof techniques. So rather than trying to show people that, oh, look, here's my code, you hopefully don't find any problems with it. You actually just prove everything must be correct. And there's a software development method called Cleanroom, which is where you do this kind of formal verification. So this is sort of the ideal inspection, which realistically can't happen all the time, but when you can, it's kind of neat. And the idea here is that you use static verification. That is, again, static not running the code, but rather just saying, here is the code. I can directly show that from start to finish, it will never mess up and it will always give you the thing that it's supposed to do. So rather than finding defects, you show there cannot be any defects. And this is because you have what's called an ultra clean environment, meaning that you assume that there's not going to be any issues raised by, for instance, a certain operating system, and you say, okay, in this perfect environment where no hardware issues will happen or anything like that, the code must always work correctly and it always will work correctly no matter what. And so in addition to maybe you might still have formal inspections, you definitely will have correctness proofs where you can show for sure it works. The proof might need to be inspected, of course, but assuming the proof is correct, that means the code is right. Usually this means that the parts of software that you have are specified and verified. You don't really need to do testing, because if you can prove that everything is correct, then it's going to be correct. So just a few terms are listed on this slide that you can, I guess, review. I don't really need to list them all out, but these are all things that are specific to this idea of formal specification / the Cleanroom method. And this is making sure that your software is definitely right, no matter what, mathematical correctness arguments. If you haven't done this kind of thing, which maybe you haven't, because I don't really know what's in the discrete math course at Ontario Tech, but definitely other universities have had courses where you take a piece of code and you prove it is always right. This kind of thing is hard, but it's the kind of thing that is the most safe. If I can prove my code is right, that's better than having a bunch of tests and hoping the tests show that there's no errors. What if I don't have the right tests? There's always a risk of that. Now, going back to the lightweight approach of things, extreme programming. Our goal with extreme programming is to be as lightweight as possible, as extremely agile as possible, which means that any kind of traditional inspection where you have a bunch of meetings slows down, lots of bureaucracy. No good. We can't do this. So we have two practices that we do. One is called pair programming. One is refactoring. Pair programming, so you have two people usually sit next to each other, one codes, one watches. I guess they don't physically have to be next to each other, but one person is coding, they're the driver, one person is watching, they're the navigator, and the navigator is responsible for the high level, is what they're doing correct? Will this lead to a successful piece of software? Are there issues that they're going to run into? And the driver is just focused on the now. Here is the code I need to write to do the thing at the moment. And the navigator and driver are supposed to communicate with each other to make sure that what they're doing actually makes sense. So, benefit of pair programming is it's immediate. If there is an error introduced, you see it right away. So you're less likely to have things like typos because the second person will say, hey, you made a typo, and notice it more often. So it's shown to improve quality, shown to improve productivity. Quality because you're inspecting all the code as it's written as opposed to waiting until later. And productivity because you don't have to worry about switching back and forth between things because the navigator is only focused on sort of the high level understanding and the driver is only focused on the code level of writing things. So you don't have to worry about switching back and forth between, okay, this code does this, but do I need that for the whole program to work? That's not really the issue. Yeah, so here's, I guess, the two roles. They say driver partner. I've heard driver navigator. The terms are less important. Always one person is coding. They're doing the immediate coding task. The other person is thinking about things. So this replaces paraphrasing because they're just thinking in their head, here's how the code will work. And the partner / navigator will look for any errors that are going along. And so you don't need to use a checklist because you have the person to be your checklist for you, which is kind of handy. Okay, code paraphrasing. This is a really good skill to develop because anytime that you're writing code and you want to explain it to somebody, it's often good to be able to do it without using coding terms, which is a skill that is very hard to pick up. So the original FIGAN inspection, that's what we were talking about last class with the really formal process, code paraphrasing is the original idea for reviewing stuff. And the idea here is that you take the lines of code and talk about it in terms of what it's doing, not in terms of programming. You don't speak in terms of variables. You say, this code solves this part of a problem, for instance. And the idea here is that you make sure the code is actually doing what you say it does. So you don't mention variables, you don't mention control flows, so you should avoid saying, if this, else this. You should say, in these scenarios, here's what the code does. In these scenarios, here's what the code does. So it's all in a more abstract sense. And the idea here for any kind of discussion is about scenarios. If I want to do a thing with the software, here is what should happen. And you don't say, if I want to do this, then I declare this variable. Like, as soon as you start talking about variables, you're already not paraphrasing, you're just reading code. So paraphrasing is often combined with checklists. The checklist is usually addressing the specifics of the code, how many lines does it have, or variables declared before use, that kind of thing. And the paraphrasing is about the meaning of it. So I think if we did have class discussion, which unfortunately we missed, maybe you could talk about it in the Slack if you really feel like it, maybe. And so here is a program. It is written in code. So if you were to explain what this program did, how would you do it? It's all code here. I won't give my own interpretation. That's something for you to try out. Maybe you can share with others what you would say this code does. And if you want a little tip, the code's also wrong. So not only do you have to explain what the code does and what problem it's supposed to solve, but you also have to figure out what is the mistake in here, because there is a mistake. So if you can figure that out, let us know in the Slack. I'd be interested to see if anyone can figure out what the problem is. Okay, refactoring. So what is refactoring? This is a super important thing that you'll want to know. And it's the idea that you can improve code without changing what it does. Looking at both code and design, there are ways that you can redo a program where none of the behavior changes whatsoever, but it is simpler and better in doing the exact same thing. With extreme programming, it's supposed to happen all the time. Anytime you change the code, you ask yourself, can this be refactored to be better? And it tries to keep things as simple as possible. Sometimes that means as short as possible, but not if it means making the code confusing. So there are a bunch of rules that you can follow and a bunch of patterns, which are refactorings, ways that you can consider changing the code to adhere to some of the rules that we're going to talk about. So in extreme programming, best design, the simplest design. We want to keep things as easy as possible, and there are a few constraints that we want to follow all the time. First off, the whole system, which is code and the tests, communicate everything you want to communicate. So anything that's in the specification, anything that's in the solution should be present in the code. If something is missing, that's a problem. So, obviously the shortest program I could write is no code, but now nothing happens. That's not ideal. Now, in addition to having everything you need to have as part of your code plus tests, you also should have no duplicate code. This is often the hardest part, and the thing that I see a lot of programmers mess up the most times is that they'll have multiple parts of the program doing the same thing and copy paste big blocks of code into each part. You don't need to do this. There are ways around it. In general, the system should try to have the fewest possible classes. This doesn't mean put everything in one class, because that is, I guess, technically speaking, the fewest possible classes. But what it means is that you shouldn't have excess classes that do very little. When you're at the point where you have a class and the only responsibility of that class is to hold like 2 variables, ask yourself, do you really need that class? Maybe it's better to have it as some other kind of object. It also should have as few methods as possible. If you have a method that barely does anything, ask yourself, do you need this method? And the idea here is that you want anybody who's looking at your system to need to understand as few classes and methods as possible to understand how the whole system should work. Sometimes this still means you have a number of classes because it makes sense to have them. But you shouldn't have, a whole bunch of, like a ton of classes. Maybe you have one class for every single thing a person can do. That's probably excessive. You could probably cut down on that with a different strategy. Now, the first two of these points, doing everything that needs, communicate everything you need to communicate, having no duplicate code, constitutes what's called the once and only rule. So everything that must be in the program is in the program, but it's only in one spot. You don't have multiple lines. So how do you do refactoring? We're going to need 5 things. We need the code to refactor, of course. We need tests, because once you're done refactoring, you need to make sure you didn't break anything. If you broke something that you didn't refactor it, you just messed it up. That's no good. You need a way to figure out what are the things that need to be improved. So why are you refactoring? How you're refactoring, so a set of templates that will change the design but not affect how it works, and know how to apply them. And finally, a process to actually follow. How do you know when to stop refactoring, for instance? Okay, so here is a whole ton of code. In short, let me paraphrase for you what this code does. There's kind of a little comment here that sort of illustrates it, but it's a little vague. This code is supposed to take some text, and inside the text are going to be the strings %code% and %altcode %. And the idea here is to go through, find where these symbols, these strings are, and replace them with the appropriate other files or text or whatever is supposed to be in that spot. Now, the code here is a mess. I don't even think I want to explain it because it is so confusing as it is. You have a class, it's called code replacer. It's got some variables. There's a method called substitute, which is supposed to do this operation. But this method, substitute, it starts here, goes all the way to the end of the slide. This is all still part of the substitute method. Oh my goodness. So this code sucks. And how do we know it sucks? Well, we can say it smells. And this is not a joke, this is actually a technical term. So a code smell is a bad sign. It's an indicator that the code probably could be better. Here are a few things that might indicate your code smells. Some of the classes are too long. Some of the methods are too long. You have switch statements. Most of the time switch statements can be replaced by polymorphism. So instead of, if it's a bird, else if it's a cat, else if it's a moose. Like instead you just have like subclasses for each of those things, and you use polymorphism or abstraction to eliminate the need for any of these switches. Struct classes, so classes that don't really do anything and just store data, for instance, should be avoided if you can. Duplicate code is the big one. Almost duplicate code, it's like literally the same, but maybe like one thing is different. You can probably work around that. Having too many primitive type variables, if you have excess variables you simply don't need, maybe some of these should be constant, maybe some of them should be just removed completely. Useless comments, this is of course a big one because a lot of programmers don't know what's clear and what's not. You should only comment things if they need to be explained, not every line. And of course there's many more. So, to do the refactoring, we have 3 steps. Find the code that smells, refactor to improve it, run our tests again to make sure we didn't break anything. And this is repeated until we're done. So we're done when everything still passes the test, we haven't broken anything. Everything is communicated, we didn't remove any parts that need to be there. No code is duplicated, and we don't have excess classes or anything like that. There is refactoring.com as a source if you're looking for ways to refactor your code. There's also a book you can get if you really like, but all this stuff is of course publicly out there if you want to look it up. Now, here's probably the most common and most useful example of refactoring. It's called extract method. This is really important if you have duplicate code. So what happens? Given some code, so here's some code over here, it computes a score. Suppose you compute this score about 50 times in your program. Do you really want to copy and paste this whole block that computes the score in all those 50 places? Probably not. Probably better to just have a method called compute score. And what does compute score the method do? Everything in this code block. This way, every time that you need to run these lines of code, rather than having to copy paste it everywhere, you just call a method. And the method handles everything you need to do. Hence the name extract method. Now, what smells in that example I showed you earlier with the code replacer? Well, the class was super long. Because it was a long method, which is really obvious, There are a few variables in there that were used in the method but not really useful elsewhere, so why do they need to be outside of the method? They don't. It's tied to using the file system, that kind of sucks, and there's a lot more. So how do we fix it? We pick one refactoring, we apply the refactoring to change it, we test to make sure nothing's broken, and then we keep going. So let's give it a shot. Okay, the worst one is substitute. So our substitute method is super, super long. It does like a million things. And so to cut it down, we're going to take a chunk from it. And so this one's called read template. And I think generally the idea here is that it's reading in some stuff and then returning a template. And so this will help to cut down on the substitute method by moving some of the functionality elsewhere. A lot of these variables that we're working with don't need to be present for the rest of the method, so we just move them into their own, called read template. Make sure everything works after we cut this out, and then we test it, and if everything is good, then great, we can move on. Now, let's take a look here. So where was this one? This one was from, yeah, okay. So introduce explaining variable. We can improve the method that is in these slides here using a refactoring called introduce explaining variable. And the one that we're introducing is, I believe, it's this template name. So over here, where you see my, yeah, you can see the little red thing. There's a line that says make a new file reader, and the file readers needs to have the directory of a template plus template.html. This is like convoluted. Where did you even figure this out? I only know this because I've seen these slides before. So this thing in the parentheses here seems like magic. Like, where did this even come from? So rather than trying to write a comment in here and explain what's happening, we just add a variable, and the variable here is called template name. And we get the template directory, and we add template.html, and so that's the name of a template. And when we open our little file reader, we just give it that name. So now we have what is the file reader taking as a parameter? Oh, it's taking the name of the template as opposed to taking something from somewhere. Okay. Inline temp. So over here, we make a file reader with the template name thing, and then we pass it to our buffered reader. A whole bunch of readers that are going on here. Don't worry too much about understanding like the nitty-gritty details of the code. We just really are concerned about trying to cut it down and minimizing how much extra stuff that's here. So the way that this buffered reader thing works is it takes the file reader as a parameter. But we don't actually really need it again. So rather than actually having these two separate lines here to open all these readers, we'll just merge them into one. And so when we make our buffered reader, we take the file reader as a parameter inside the same line, so we cut down on an extra line we don't need to have, shortening the code. Again, we test it, make sure this doesn't break anything. Maybe not doing the close of the file reader will cause an issue, but if it doesn't, then great, we're good. Okay, now the substitute method is still too long, and if I actually go back to it, I can show you one part of it that I don't like in particular. Let me go back here. So over here, like without looking at the nitty-gritty details of the code, you can kind of see that this part here and this part here, where the two are separated into blocks by these comments, they look really similar. Template split begin, template split begin, part 1, part 1, part 2, part 2, assign some code something, assign some code something. There's a lot of overlap between these. So what if we can replace both of these blocks with some methods and parameters rather than having this giant chunk of code? So the first thing we'll do is we're going to cut a bunch of this out and make this a method. So we'll do that over here. Substitute for code. We literally just cut out that block I was showing you with the template begin, template part 1, whatever that does. Again, we don't really care too much about what it does as a class. We're mostly just focusing on the refactoring here. Now, this whole part here can replace the substitute method. So now we can just write substitute for code in our method. Again, make sure it works. And we also can improve by replacing this here. Now, having constant having constant variables inside of a parameter, very awkward. Not an ideal thing to do. You generally shouldn't try to have some numbers just in places out of nowhere. For instance, where does a 6 come from? It just seems like magic, right? It's not really good to have just like stray numbers appearing out of nowhere because no one can really understand where the heck this appears from. If you're very savvy and you've been looking at this code very carefully, you'll understand where does a 6 come from? 6 is actually a number of characters in %CODE%. Now, well, somebody reading the code might not realize that. You know, that 6 just is literally coming out of nowhere. Where the heck does that come from? So instead, we use variables to help explain things by doing a refactoring called replace magic number. Instead of just having a 6 out of nowhere and having a %code string out of nowhere, we make a variable called pattern. We give it the value that we want. And every time that we're supposed to have our something that denotes from this, we can just replace it with pattern and with pattern.length, which is 6. Again, test it, then go on. You can also do this for the other block that looks similar with the split begin, part 1, and so on. That giant block was only different by a few different pieces of code. Notably, it has alt code instead. Again, we can also replace the magic number. If you go back, you'll see that the original code here has a 9. Where does this 9 come from? %ALTCODE % is 9 characters. So we'll do the same thing. Replace this magic number with the length of the string and replace this just stuff in quotes with a variable called pattern. Okay, now, because this method and this method, if I bounce between the slides, they look almost identical, right? There's so little difference between the two of them. So I can just make a single method that does what they both do and add some parameters to help distinguish between them. So we call this Parameterize Method, where we combine two methods that are almost the same, duplicate code, not what we want, into a single one. And all we have to change for them is the pattern's going to be different, for instance, and one of them is going to use a printer to write some stuff out. Does that even show up in here? It should. It might show up elsewhere in the substitute. But anyway, we keep doing this over and over, and eventually we end up with better code. We follow the rules, we always test every single time to make sure we didn't break anything. And when we're done, we end up with this. Here's our code replacer class. It's got a little constructor, so it can read in a template. And now the only variable that's held by the class is this template, the thing that we're using to help replace this stuff, the % signs and things. The other variables that were here are moved over into the methods that actually need them. We have this read template method that we made. This one reads stuff in, it's shortened, doesn't have as much stuff in here, and eventually reads us a template that we need. Here's our substitute method. Look how short it is. Before it was a page and a half, and now it's just this little tiny length here. We call the substitute code method up above a couple times, which replaces those giant chunks. And those chunks have been shortened out into this, where now we have just a little bit of code. We still do everything that we did before, so the behavior of this is exactly the same as the other code. Just this time, the first time we call it, we pass it %code %. The second time we pass it %altcode %. And otherwise, it does exactly what we desire. So, in summary, code inspections, when applied to code, there's lots of different things you can do besides the super formal stuff. There's checklists, there's paraphrasing, walkthroughs, and so on. With lightweight practices like we use in XP, we want to get the benefits of code inspection, namely being able to see the error and not see the failure, which are two different things. The error leads to a fault, which leads to a failure, sometimes. And the failure is just, okay, a thing is wrong, but you don't know where the problem comes from, whereas with inspection, you see this code is incorrect, you need to fix it. Heavyweight practices go the other way. You have these formal inspections like we talked about, and you can go all the way up to proving that something is correct, which is nice to have. Practically, it's very hard. So XP, which we're using for our project, continuous lightweight inspection. We have things like pair programming. We have things like refactoring. Refactoring is also done outside of just the XP context. This is actually done in pretty much any major software company, which is taking your code, not changing the behavior, so it's super important to always test every time you change it, but making the design better, easier to read, more understandable, and so on. And you do this one step at a time. You always test to make sure that no failures are being introduced by your refactoring. That's it. I think I managed to get through in a short enough amount of time. You can always go watch if you want me to go over anything again. Let me know if there's any questions on Slack. I'll be happy to answer. The slides are the basis for this week's quiz, so make sure you don't miss it. And I will see you all in class. Thanks for watching. Bye-bye.